When the United States sails from New York to London, the entire Atlantic Ocean is actually disturbed by the ship. Similarly, an airplane in flight disturbs all the Earth's atmosphere. Intuitively, however, we feel that only a small part of the ocean is important to the ship and a small part of the atmosphere to the plane. Here, a thin plate is towed longitudinally through a tank of very viscous liquid at slow speed. Observe that all of the particles in the field of view are set in motion, although with decreasing speeds far from the plate. Now the plate speed has been increased, yet the particles far from the plate no longer appear to move. Actually, they are moving at least as fast as in the previous scene, but the camera speed has been increased to prevent blurring the action near the plate. The lengths of the red lines are proportional to particle speed. It may be reasoned that there is some fluid particle speed, so slow compared to the plate speed that particle motions at slower speeds may be entirely neglected. This speed is usually taken as about 1% of the plate speed. If a bounding line is drawn to include the fluid particles whose speed is 1% or more of the plate speed, the region bounded by the line is called the boundary layer. You are now moving with the plate so that the undisturbed fluid appears to be moving past the plate. The lengths of the red lines are still proportional to the relative fluid speed. The boundary layer is identical with the previous case, but it now has to be defined as the region within which the fluid speed is less than 99% of the apparent stream speed. The boundary layer grows thicker with distance from the leading edge. The growth rate is not linear, however. The boundary layer becomes thinner if the velocity is increased. If the viscosity is decreased, if the density is increased, or if their ratio, the kinematic viscosity, is decreased, the boundary layer also becomes thinner. When these factors influencing boundary layer thickness are combined, we find that the dimensionless boundary layer thickness, delta over x, depends inversely on the Reynolds number formed using the distance x from the leading edge as length parameter. By theoretical calculation, delta over x is approximately equal to 5 over the square root of Reynolds number. In air, boundary layer development is the same as in liquid at the same Reynolds number. Identical laws hold for all fluids, whether liquid or gas, at least as long as the fluids are incompressible. Boundary layer velocity profiles are produced by shear action between adjacent layers of fluid. The magnitude of the shear stress is given by Newton's law of viscosity. shear is eventually transferred to the plate surface, where it is felt as drag or skin friction. Theoretical calculation of dV by dy at plate surface permits evaluation of the wall shear stress at each x distance, and drag is obtained by integration over the plate of length L. Drag is conveniently expressed in terms of a dimensionless skin friction coefficient, C sub F, and this coefficient is a function of Reynolds number only. The flows we have been looking at are laminar flows, but laminar flows and their associated theoretical formulas cannot be extended to arbitrarily large Reynolds numbers. Rather, the boundary layer becomes thinner at a given x distance as the velocity is increased or as the viscosity is decreased. And the shear stress or friction at the wall increases until the boundary layer bursts into turbulence. Turbulent flow is characterized by random whirls or eddies as opposed to the smoothness of laminar flow. Turbulent, laminar. Watch the boundary layer become turbulent as the plate is towed past the camera. Again. The upper boundary layer in these pictures has been made turbulent by placing sandpaper on the plate surface to create a disturbance. The lower boundary layer is still undisturbed and laminar. Turbulence can be generated in the boundary layer by disturbances only if the X Reynolds number is greater than about 100,000, so that close to the leading edge, the boundary layer must always be laminar regardless of disturbances. A transition region of intermittent turbulence connects the laminar and turbulent portions of the boundary layer. Observe that the flow outside the boundary layer is undisturbed and laminar. But even if the outside flow were turbulent, a laminar boundary layer would originate near the leading edge, becoming turbulent later. Outside disturbances influence the location of transition. By carefully avoiding disturbances, transitions can be delayed to Reynolds numbers of several million. Here, a turbulent river flows over a dam. A boundary layer originates on the concrete surface at the top of the dam, becomes turbulent, and thickens until it reaches the water surface where it becomes visible, because the small, intense eddies of the boundary layer turbulence entrap air from the atmosphere. The original river turbulence is invisible because its eddies, which originated on the riverbed far upstream, have decayed. A turbulent boundary layer is thicker than a laminar boundary layer at the same Reynolds number, and velocity profiles are much flatter in the turbulent case. shear stress is no longer given by Newton's law of viscosity. Between the turbulent fluid and the plate, too close to be seen clearly in the picture, there is still a laminar sublayer in which shear stress can be calculated by Newton's law. Velocity gradients and shear are very large in the sublayer, so that the skin friction coefficient exceeds that for a laminar boundary layer at the same Reynolds number. Since the boundary layer near the leading edge of a plate is laminar all of the time, the integrated drag on the plate is made up partly of laminar and partly of turbulent friction after the boundary layer becomes turbulent. Because transition depends on the disturbances that are present, there may be more than one value of the skin friction coefficient for a given Reynolds number. However, when transition occurs near the leading edge of a long plate, friction of the laminar part is negligible compared to that of the turbulent part, and there is a unique relationship between skin friction coefficient and Reynolds number. Boundary layers also develop in the entrance region of